Hello and welcome to ROS 101 Fun Approach delivered to you by Summer. Just a quick recap on what we did so far. We were introduced to Gazebo and we managed to launch one of its worlds. And we managed to launch, for example, the house world and the empty world and the Turtlebot 3 world. So we define worlds as environments that include a number of models and have some settings like the lighting, the shadows, the transparency, and different components like models. And we managed to spawn our robot, which is Turtlebot 3 Waffle Pie and Turtlebot 3 Burger, into the simulation. So today we're going to define something called localization, also mapping, and SLAM. And we're going to get introduced to each one of these terms, and we're going to have some basic definitions and like the simplest form of explanation for these three terms. And we're going to launch the gmapping package in Gazebo, and that is a SLAM package, right? And then we're going to draw a map using a robot's LIDAR. So we're going to draw a map for the environment or for the world we're located in, using a robot's LIDAR, and we're going to define what a LIDAR is. So let's dive in. So before getting our hands dirty, we need to get introduced to some theoretical terms that will be quite useful for us and are quite important to understand and comprehend. So first of all, we have something called localization, and for that we'll assume that our robot is here. So it's located somewhere here in my world, and let's just assume that the global reference frame of my world is here. So we've got like our x-axis, our y-axis, and we've got the z-axis pointing out of the page. Alright, so we always assume that the height of our robot is 0 since our robot is located, on ground level. Alright, or it may be just like translated a little bit in the z direction depending on where the center of our robot model is. But anyway, we can assume that the z distance or the z coordinate of a robot is always 0 when it comes to wheeled mobile robots. Of course, that's not the case for other mobile robots like drones, for example, quadrotors, which have like variable height depending on the thrust of its thrusters. The same thing goes for autonomous underwater vehicles or remotely operated underwater vehicles, which have 6 degrees of freedom underwater, unrestricted. And there are also many types of robots. We got humanoid robots, for example, and actually their center is always oscillating like in a sine wave fashion, because the center of mass like follows a sine trajectory or an almost sine trajectory during walking. So we'll assume we have a wheel mobile robot here, so our z coordinate is always constant, but our x and y coordinates are variable, and they change during the simulation. So one of my tasks as a ROS developer is to develop some module called localization module. So the word localization means is to determine my global pose relative to the global frame. So I need to determine my global x, I need to determine my global y, and of course I need to determine my theta, which is the yaw angle. The roll and pitch angles are always assumed to be 0 because we have like some restriction forces, which are the ground reaction forces, because we have like 2 actuation wheels and 2 caster wheels. And what a caster wheel is, it's like a support wheel here. So we always have like the main wheels, the right and left wheels, which are responsible for actuation and motion, and 2 caster wheels, which look like your stroller wheels or like supermarket cart wheels, which which do not help actuate your vehicle. They're just there in order to provide support, and they have like multiple degrees of freedom, so they don't restrict any motion. They're just here to support the vehicle so that the vehicle does not tilt forward or backwards. So we can assume that the roll and pitch angles are always 0. Right? So this is what's meant by localization. And in order to localize our robot here, we need to have a map. So we need to have a predetermined map for this environment. And by map, I mean like we need to have some 2D map describing the location of walls, for example, and describing the location of objects, like this, for example, right? So our map basically is going to be, like a whiteboard with some black lines or black areas, where these black areas determine the position of obstacles or the coordinates of obstacles that the robot is not supposed to, go through or collide with. And by knowing our map, we can localize the robot. How? The robot has some sensor here called a LIDAR. So what a LIDAR does is that it produces like laser beams, all right? And once these laser beams hit some object here, the laser beam retracts here and gets back to the LIDAR, and the LIDAR computes the distance to that object through the computation of the time of flight. It's basically like sonar. And the LIDAR is rotating, so we've got a family of LIDARs called 360 LIDARs, which produce several beams in all directions, in all the 360 directions, or 360 degrees. Sometimes LIDARs just, like send beams in a span of 180 degrees instead of full 360 degrees, but let's just assume that we have a LIDAR that produces beams and keeps rotating. It's like shooting laser beams and rotating at the same time. So we get like a local map which determines, the current observations in my environment, the current depth of objects that I've located so far. And this laser beam has a range. And what I mean by range is the maximum length of this laser beam, after which I'm not able to compute the distance to the object. Maybe the object is too far and I cannot locate it. So whenever I'm walking, I'm just taking like 2D images of my current environment, and I'm trying to determine the black dots or the obstacles in this environment while I'm walking or while I'm moving, right? So by knowing this map, we can determine the location of the robot. And for example, let's just say the robot was here somewhere, right, in my environment. So my first observation was that I found like a wall here, right, thanks to my rotating LIDAR. And during one span of the LIDAR, I just detected these walls, for example, right? So when I moved a little bit and the robot changed its position to be here, for example, so the robot was basically moving forward and the robot became here, I take another set of observations, and this time my observations reveal that the walls are getting this wall, for example, here got closer to me, because this is a relative measurement. You getting closer to the wall is equivalent to the wall getting close to you while you're static. It's like the train observation effect, right? So we found that the new readings, well, this wall didn't move, and this wall is like getting closer to me. And I can deduce through this observation, or by comparing the two observations, the past observation and the current observation, that the robot has moved like a distance for example, if this wall got closer by, for example, 1 meter, then that actually means that the robot has moved forward for 1 meter. And this is a pretty simple explanation of what's going on. It's actually a bit, more complex than that, but this is a simple example to let you, have the intuition of what's going on. So this is how localization works, right? There are other sensors that, are subsets of this localization process as well. You might have an IMU, right, which computes the acceleration. And the IMU, through this computation of acceleration, you can double integrate this acceleration value in order to get an estimation of how much you moved. So, for example, your IMU is noisy, so it will give you a reading that basically says that the robot moved, for example, 1.2 meters instead of 1 meter. Because as we said before, any process that includes integration is called odometry or dead reckoning. And integrating the reading of the IMU is one of these dead reckoning methods. So we've got the reading of the IMU, which says, for example, that you moved 1.2 meters. And we've got actually the reading of the LIDAR itself has some noise embedded into it, but the noise of the LIDAR is quite small because we call this sensor like an update sensor. And update sensors or update measurements have a high level of accuracy, but they have lower frequencies. Like I get an update every lengthy period of time compared to an IMU. So the IMU gives a reading like every, for example, 0.1 second. But the LIDAR would give you, say, an update every 1 second. Right? So you have a compromise between accuracy and speed or frequency. Alright, so it's a compromise of two things. We also have another source of dead reckoning, which is the encoders. Right? The encoders are sensors that are attached to the wheels and compute how many revolutions did these wheels make. So by computing the number of revolutions, we can have an estimate of how much we moved. Or we can compute the velocity of the angular velocity of these wheels, and by integrating the angular velocity of the wheels, we can also have an estimate of how much we moved. Using encoders is better than using the accelerometer of the IMU because instead of double integration, you only have to do single integration. But still, there is some noise embedded into the encoder reading because the encoder is not a perfect sensor. It will not compute the number of revolutions very accurately because sometimes the robot is moving too fast and sometimes the sensor slips a number of counts. Right? So what we do here, what the localization process includes, is that we compare, for example, the readings from all sensors against each other, and we compare them with the map readings. So we got the map, which is the source, and sometimes we got something called a prediction. Alright, so what this prediction means is practically any dead reckoning source. And sometimes, when we don't have any prediction sensors, we use the dynamic model of the robot in order to have an idea of where the robot is right now. So by knowing the mass of the robot, and by knowing the diameter of the wheels, and by knowing the specifications of the DC motors that activate these wheels, I can have an idea of how the robot or how the dynamic model of the robot works, and then I can have an estimation of, for example, if I provided a voltage V for a number or for a specific period of time t, then I can substitute with these values, or I can plug them into the dynamic model and get an estimate of the position of the robot right now. So that's another dead reckoning method, right? So through information coming from the map and information coming from the prediction, right, we can have a product which is the location of the robot or the localization of the robot, right? So localization assumes the presence of a map. So that means that the map is already there, and the map was drawn in advance. So I'm not using the LIDAR in a real-time situation. I've already used the LIDAR and I've just drawn a map for the entire place or the entire environment, and then I'm using the static map, and by static map I mean a map that was prepared in advance, right, in order to localize the robot. So by comparing information from the map and information from the prediction, right, we can estimate the location of the robot. So this is pure localization. And sometimes I might depend only on data coming from the map, say, right? Yeah. No, sometimes no, it has to be prediction included as well. So by these terms, all right, are used for the localization process, or the terms that are involved within the localization process. We have another process called mapping, which is the reverse of what we just said. So let's clean up everything. Right, mapping assumes that we have the location of the robot in advance. So there's some very accurate sensor that gives us the global location of the robot. All right. Whenever we're moving, we have an accurate estimation of the current location of the robot. So localization is covered, but actually we don't have a map. All right. So let's just assume we have some sensor like a GPS. And let's assume that this GPS is very accurate, right? So this GPS gives you an online feedback of your current global pose, all right, without needing a map. So the localization part is covered, but you need to make a map of the environment. You need to map the environment, all right? And this process is called mapping. So we use our LIDAR sensor in order to have some observations, and we're trying to gathering all of these observations during some span of time, and we're going to group them together. Right? It's like that shot in the Iron Man movie when Iron Man was showing his design when they were imprisoned in the cave, and he was showing his design to the other scientist. I think his name was Jensen, I guess. And what Tony Stark did is that he had multiple drawings or multiple layers of drawings, and he had to overlap them together in order to give the big picture, or the entire suit view. All right. So I don't know if I can get that in YouTube in order to let you have an idea of what I'm trying to say. It's kind of weird, but it will help you understand what I'm trying to say. So let's just say Tony Stark, for example, Mark 1. And yes, I'm a Marvel nerd, right? So I think it was that one. No, not this one. I think it's yeah, I think it's this one, but of course ads.
You could get a
Another ad.
5% deposit. Wait, what?
I hope it's the one, because I don't like ads. Right, so they're working on the arc reactor here, and he was trying to power his suit. So yeah, this is where he brings the layouts of his project, and he's got multiple observations, right, or multiple maps, and he's trying to put them all together, these individual observations at different spans of time with different robot locations, and he's trying to overlap them together in order to get a full picture. All right, so this scene illustrates what I want to say. So we've got multiple observations. So let's say that the robot had an observation here. So this observation looks like, for example, if we include it in a separate drawing, then that is the current observation. All right, and the robot location is, for example, here, for example, here. So let's just say that the robot moved here with its face having an angle theta like that, so its face is like this. So we will have another observation, and since this robot now represents the center of my individual observation, so I'll get an observation which looks like that. For example, something like this, and something at my back. Maybe it will look a little bit like if I'm facing the robot like this, so we'll have something like this maybe. Yeah, it will be something like this. Alright, and I move forward again and I move like here. Sorry, so the face of the robot is here. And I get a third observation, right, where the robot is basically like having an observation which looks like this, right? So for each one of these observations, I got a record of the robot location. So I know that the robot here was like looking that way, and I know that here the robot was looking somewhere like this, a little bit rotated, and here the robot was looking here, for example, right? So by overlapping the robot locations in each of these observations, so I get all of these images or all of these individual local maps, and I overlap them together in order to get a very strong map where, for example, this is the robot pose after overlapping. So I got all the robot poses to overlap together into, you know, a single entity here, and then I get a very strong right, I get a very strong like drawing or a very strong belief in the location of the obstacles. So too many obstacles are overlapped together, and then I know for sure that the global map has the obstacles, for example, here. Alright, so this is what mapping is all about, and it assumes that localization is covered. So you either have localization covered and mapping missing, or mapping is missing and you need to have localization active or have a localization module. So what if I'm navigating through an environment that I know nothing about, and at the same time I don't know where my robot is? I had an idea where I placed it initially, but I don't know where the robot is hitting right now. So this is called a problem of SLAM, which is short for simultaneous localization and mapping. So let me just play some stuff. And the problem of SLAM is a complex problem because you're trying to, you know, get localization from mapping, which does not exist, and get mapping from localization, which also does not exist. So this is crazy, and it's a complex subject that would require, you know, a separate lecture on its own. But let's just say that by fusing the data coming from different sensors, we could obtain what you can say is, you know, a sensor fusion paradigm, and you can determine the pose of the robot, right? Maybe not accurate at first because you're trying to construct the map and your localization belief at the same time. So they're both gonna depend on each other or rely on each other, and they're both like quite vague at the beginning. So you'll start with a pretty low accuracy, then you will converge eventually to a strong belief. So unlike the other paradigms, localization or individual localization, individual mapping, you start from nothing and you try to build both beliefs, which is the pose belief or the localization belief and the mapping belief at the same time. So it's going to be quite poor in the beginning, and then you try to improve the localization accuracy and the mapping accuracy by making them rely on each other, so they both support each other. Once you have a new information that could, you know, improve the map, that will simultaneously improve the localization. So let's have an example where the robot is navigating and we've got our set of sensors. For example, the LIDAR sensor for update and some dead reckoning sensors like the encoders or the velocity or something like that. So what you do here is first you take a shot or a LIDAR shot, so you get like a local map, right, that's attached to the current location, right? The current location is unknown, so I just say that the current location which was unknown, had a local map, for example, with this LIDAR shot, right? So later you will you will have some prediction of where you are now. So you'll say that according to my dead reckoning sensors, I moved like 1 meter, right? And this 1 meter is quite noisy, right? But it's the best estimate I have so far. And then I had another shot here, which indicates that this wall is now at a distance of like 0.9 meters, which means that I most likely moved a distance which lies between 0.9 and 1. Right? So through some sensor fusion paradigm, I can now say that the robot moved a distance, all right, which with an estimate that is better than both the individual reading of the LiDAR and the individual reading of the dead reckoning sensors. So I'd say that I moved like 0.95 meters, for example, relative to my first location, right? So I begin to denote my first location as, the center of the global map I'm trying to develop. And I'd say that I moved 1 meter or 0.95 meters from that particular location, right? And since I moved 0.95 meters from that particular location, all right, so I got a new location. So the mapping process kind of intervened with the localization problem. But I still don't have quite a global map. I just constructed a part of the environment according to my current observations. So let's just say that my entire map was something like that, and I just, mapped a small part of the environment. The environment would actually look like something like this, for example. Right? But I just mapped that part for now. So this is like a partial map. So whenever I keep going, all right, my localization sensors could help me like determine where the new obstacles are. So if I know that, for example, I moved right here, so my new local map says that I moved like, for example, a distance of 0.5 meters to the left, and I rotated with a theta that is equal to, for example, that makes like 120 degrees, for example, right? Then I got a new shot, and this new shot looks like something like that, for example. All right, and I know that my old observation was this shot, for example. So my localization module, or the localization part of my algorithm, now said that I moved like 0.5 meters to the left and rotated with, for example, 120 degrees. So based on this localization data, I can like reorient the new observation to, map it to my global map. All right, so I've got a local map, which is the local observation. I got some global map that I keep building through individual observations. So in the global map, the first observation was recorded right here. And according to this new observation and according to the localization data I got so far, then I can deduce that indeed this observation can be mapped to the global map to be somewhere here. Which kind of matches what the actual physical map looks like. All right. So I'll continue building this map and localizing myself, and the more I localize myself, and the more I map the environment, then my belief in both localization and mapping will grow stronger, all right? And this is a pretty, intuitive understanding of what's going on, because actually this is a pretty complex algorithm that is based on probability distributions and, something called particle filter, and we'll go through that, all right? But right now, we'll just do with what we have so far, and we'll try to implement those algorithms in Gazebo simulations. In fact, we're not going to write the algorithm ourselves. It was already written by some ROS developer who was working on some R&D department, right? What we're going to do as engineers now, we're going to like implement that without having to know what the black box includes, we're gonna have a simple idea of what is going on. But the details of what's going on and the entire mathematics behind the stuff can be explained in another course. All right, so that's the end of that part, and we're going to explain more as we're progressing through the simulation itself. So I got back here to my e-manual. This is the page that we finished, and we're gonna head to the next page, which includes the SLAM simulation. Alright, so here we're on the SLAM simulation page. So the SLAM, as we said, is the simultaneous localization and mapping feature. Alright, and there are multiple algorithms that do SLAM. Alright, so SLAM is not like one algorithm, it's a family of algorithms that do or does simultaneous localization and mapping. Alright. So first of all, I'm gonna launch spawn my Turtlebot burger into a Turtlebot 3 world. So I'm gonna open up my terminal here, and I'm gonna export the model, which is burger for now. So I'm gonna copy that. I'm gonna paste it here. Right. Then I'm gonna launch my Turtlebot 3 world. I'm gonna paste that here. And again, if you're running this for the first time, it's gonna take a little longer than it did here. Alright, so this is my environment. What we need to do now is to run the SLAM node. Alright, so in order to run the SLAM node, we need to open up a new tab in our terminal. And we also need to redefine our Turtlebot 3 model, because that variable is like tab specific. So whenever you open up a new tab, you have to redefine it. And you will launch the Turtlebot 3 SLAM package, and you're gonna launch, or you're gonna, run a certain file called Turtlebot 3 SLAM that launch, and you're gonna determine your SLAM method to be gmapping method. There are other methods, but the gmapping method is one of the most famous methods and one of the most widely used methods. So it's like the standard method for most ROS developers. So we're gonna go with that. All right. So first of all, as we are navigating through this package, all right, we need to look through its details. So I'm gonna head to the other locations: computer, opt, ROS, Yotic, and the share file, which includes all the packages. And then I'm gonna look for that TurtleSim SLAM, or Turtlebot 3 SLAM, sorry. So we've got a number of files. We got a launch file here, right? And you can find here that there are multiple SLAM methods. So you've got the Hector method, for example. You've got the Carto, which I think is short for cartographer. All right, and you've got frontier exploration here. Yeah, here's cartographer. All right, so we're gonna go with the gmapping package, or the gmapping launch file. So you gotta have a parameter. This is why we need to determine the Turtlebot 3 model here, right? Because it's a variable here, so that variable has to be defined in our terminal before we launch this file. And someone might ask, why am I launching this, or why am I choosing my robot model? What does this have to do with the SLAM problem? So a short answer to this is that you have a LIDAR, and the LIDAR can be attached to several locations, or one of different locations on the chassis or the body of the robot. So that differs according to the mechanical design of the robot. So the location of the LIDAR and its distance from the robot origin is different for each robot. So you got geometrical differences. So you need to determine your model in order to have the proper transform that's going to transform the LIDAR readings, right, which are reference to the origin of the LIDAR itself, or the frame of the LIDAR itself, to the frame of the robot. All right. So the LIDAR frame does not have to be coincident with the robot frame, and this is one of the differences that you have to bear in mind. All right. right? And you're gonna set something called a base frame, and the base frame is basically, is like the origin of your robot. Your robot has some local frame or some body frame, as we said before, and this local frame is attached to some origin located, somewhere in the body, all right? So this has to be determined. And you got the odometry frame and the map frame. So the map frame is like the global map frame, all right? And the odometry frame is, well, where your odometry sensors are. So basically, for example, if you have like an encoder and this encoder is producing like, some readings and you're converting these readings, right? Reference to some frame, you have to determine the exact transform between the odometer frame and the base frame, right? So you have to define the frame of each sensor, right? And you gotta relate them to the base frame, because eventually you need to reference everything to the base frame of the robot, not the individual sensors, but the base frame itself, so that we can have all the readings consistent and reference to the same local frame, right? And then we're going to compare this local frame again with the global map frame. So there are a lot of frames, and we need to define the relationships between all of them. Alright, so this is basically the same thing. We're just launching the node and determining the values. Here the values are provided, alright, whether from the terminal or here in the launch file itself. Then we're using these arguments or these parameters and feeding them to the algorithm itself before launching it. So that's pretty cool so far. So let's launch it now. So we need to, as I said before, we need to open up, run the SLAM node. So we need to copy that first into the new tab. And then we're gonna run the SLAM node here. And as I said before, the SLAM node means that you're localizing yourself at the same time constructing a map. Right, now we got something called RViz that popped up. So what is RViz? RViz is like a visualization tool that, apart from the Gazebo simulation itself, shows some particular aspects like the readings of your sensors. So I got readings here, these green readings here, I guess, represent the readings or the current readings of my LIDAR. So these are like the ends or the tip of the beam, right? So we've got some displays here that represent, for example, the laser scans. So if I uncheck that, so you find that the laser scans disappeared. So by rechecking that, we can find the laser beams that are currently, bursting out of the robot. And we can find the global map, so the global map or the current global map, because this is a global map that is, drawn by the robot itself. It's not the actual physical map, because the actual physical map would include everything in my environment. So this is the global map that is, currently constructed by the robot so far. So once the robot starts to move and it, gathers some more information or some more observations, this global map is going to evolve and it's going to include more details. But since the robot is static here, we only get to draw some part of the map, which is the part that is, included in our current observation. Our LIDAR has a limit, so we can't map the entire environment using LIDAR beams while we're static or sitting at some position without moving. We need to navigate through this environment in order to get more observations and, help construct the map or the global map of the robot, right? So this is basically RViz, and it's a pretty good visualization tool. It lets you have an idea about what's going on, maybe better than Gazebo itself, because Gazebo does not show, sensor readings, for example. It just shows a camera view of your environment. So you get to see what's happening, what would happen in the real world when you run this package, right? But RViz is more of a troubleshooting tool. It lets you see the underlying layers, the sensor readings, and the current global map that is currently being drawn into the algorithm. So when it comes to the algorithm itself, you'll find that this global map is actually some sort of a matrix. And when you look at the matrix, it's, you can type it on the terminal, but again, it would look like you're the matrix operator that is just there and reading some green symbols, and it's pretty hard to interpret these symbols. So RViz is quite useful when it comes to visualizing this global map, for example, and it lets your task become much easier. You can troubleshoot something that you can actually see and interpret with your own eyes. Alright, so let's move on now. We ran the SLAM node, so right now, as I said, we need to navigate through the environment in order to make use of the gmapping algorithm and start to have newer observations and begin to overlap these observations with the already existing observation and begin to build the global map bit by bit. Alright, so I'm gonna open up a new tab, right, and I'm gonna copy the robot model. I'm gonna paste it here, and then I'm gonna ROS launch my teleoperation node. So now I could, navigate through the environment. Alright, so my teleoperation node is now active. So we're gonna visualize Gazebo and RViz. So let's just, minimize that a little bit so that we can have a view of everything. And one thing is, I cannot teleoperate without having the teleoperate terminal open. So I need to keep all these tabs open. So let's move forward, for example. So I'm gonna give some forward linear velocity by clicking W. So I'm clicking W. You could notice here that the map is starting to look more complete. We are gathering new observations, and these new observations help me construct the map. So the locations that weren't obvious or were vague are now close to me, and now I can get newer observations, and I begin to overlap these new observations with old ones, and I'm beginning to construct a better map. And at the same time, I'm localizing my robot. Alright, because I didn't have any information about the location except the very first location that I had here, and assumed it's the initial location. So I'm referring all the upcoming locations to this starting location, and I'm trying to figure out some intuition behind my current position based on all this information that I'm gathering over the simulation time span. Right, so you can see that so far I have a pretty good understanding of my map. So I mapped most of my environment, right? But only the part of the environment that is located within the Turtlebot house or world, because you can find that this is a closed world. That means my robot is in a closed environment, so I cannot map what lies beneath these walls because this is a closed place. It's like a castle, right? So I can't possibly map the environment that or anything that lies beyond these walls, right? Because my LIDAR cannot access anything, and even if I get close, I'll just collide with one of the walls. So my biggest achievement here, the only thing that I could achieve is having a map of this closed environment. And this is pretty cool because mobile robots usually operate within closed boundaries or some warehouse or some closed environment, or as we say, mobile robots tend to operate indoors. Some robots operate outdoors, but these robots deal with more complex aspects like dynamic environments. So in this environment you get everything. Everything here, every object is static, it's not moving. But once you have moving objects, then that would confuse the algorithm, because the algorithm assumes that the robot is the only thing that's moving, right? So once something moved, it will, it may distort the localization data, because I was supposed to measure the relative distance between me and the object. So the object is supposed to be static and I'm moving. But let's just assume that the object is moving as well. So if the object is moving as, with the same velocity as me, then I would think that I'm not moving at all, right? Because our relative velocity is 0, so I cannot, figure out whether I'm moving or the object is moving or both not moving. So everything has to remain static. So that's why in the standard situation we operate indoors, but when you operate outdoors in the presence of dynamic objects like people and cars and stuff like that, the problem tends to be much more complex, and this requires a lot of research work in order to work in such environments. So this is a pretty advanced level. We're not going to go through that. All right. So I can notice that some parts are still distorted. For example, this part seems like, not completely mapped, because when something is completely mapped or when some object is completely mapped, then it's going to have like some solid boundaries, some solid black boundaries. So this, for example, I think this one is open, so I don't really know if there's a wall here or is it open. So I need to like rotate a little bit and just continue navigating my environment. So I'm going to rotate a little bit. All right, yeah, then I'm going to stop, then I'm going to move forward and rotate a little bit just to, I need to change my trajectory. All right, so I started rotating like crazy, so I need to adjust myself. Now I'll move forward, I'll stop again. Then I'll move forward here. A little bit faster. All right, stop. So we can notice that each of these cones in the middle are now like totally encompassed by black dots, except this one here and this one. But I'll get to them later. So I'll move forward now. As you can see, these open areas are now, encompassed with black dots. So I gotta have a black dot here. So I think now it's closed. And the same thing goes for that area here, which was open. Then I'm gonna stop in order not to hit the wall. Then I'm gonna rotate a little bit, the other direction. So yeah, I'm gonna move forward now. A little bit faster. And I'm gonna stop. I'm gonna rotate a little bit in this direction. And I'm gonna move forward again. Right, so I need to close up these cones here, these white cones. Then I'm gonna rotate a little bit, so I'm gaining new observations. Right, so I'm gonna move forward again. So yeah, now I need to just close these two cones here, and I think the map would be ready. I think I'll be done with the entire map. I'm gonna finish up this cone here. So yeah, I think the map is complete now. If I look, yeah, I think the aspects of the map are complete, or yeah, I think that's enough so far, right? So let's get to the next step after mapping my environment through teleoperation node. And by the way, I'm not just mapping my environment here because I'm using a gmapping algorithm. So I'm both mapping and localizing my robot, but the localization part is not, visualized here. Only the mapping part is visualized. But once you have a map like this, you can always make sure that there is some localization node running somewhere, because I cannot construct a map even if I'm executing individual mapping. Then I must have the location of the robot somewhere from a GPS sensor or something. So you can know that, rest assured, there is some localization node running, right? Whether you're doing SLAM, which is simultaneously localization and mapping, or doing some individual mapping and you have the localization data coming directly from a sensor, Alright, but since we're using gmapping, which is a SLAM algorithm, we know that we're both localizing and mapping at the same time. So let's get back here. Now I need to save my map, alright? The map was created successfully. I need to open up a new terminal, alright, and save the map by using the map server. So the map server is like a node, alright, which gives you some, mapping utilities like saving the current map that was developed so far. So there's a topic called map here somewhere. If you get to, let's just close the teleoperate node, and let's, ROS topic echo or ROS topic list the nodes that are currently, the topics that are currently running. So you'll find a map here and a map metadata and map updates. So there are multiple map topics here. These multiple map topics include information about the map that was constructed so far. If I, for example, echoed this map topic, so I'm going to type ROS topic echo map. So you'll find that there is a matrix here, and this matrix is quite huge actually. I cannot, determine what's going on actually. You'll find a number of zeros and negative ones and maybe ones. So each of these, numbers represent a certain fact. For example, -1 means this is a pixel in my map, and by a pixel I mean like a small square within my map, or a small digital portion of my map. If you're familiar with images, you know that each image is made up of digital pixels that make up the entire image. So the same thing goes for the map here. And the -1 values represent the values of the pixels, which are unknown to me. I don't know if something lies there or not, and this probably represents the areas that are outside these walls, the areas that I could not map, right? Which constitutes a very large portion of my environment, because the closed portion here is quite small relative to the rest of the environment. So you'll find that most of your matrix is made up of -1s. And then you find zeros and ones, or zeros and hundreds here. It's not zeros and ones, zeros and hundreds. So I believe, as far as I remember, I think 0 means an empty pixel, which means there are no obstacles there, and 100 means that I'm quite certain that there is an obstacle there. So this is a percentage that represents your, how certain you are that there's an obstacle in this particular location. So 100 means I'm 100% sure that there's something there, and 0 means I'm 100% sure that there's nothing there. So my belief in the presence of an obstacle in this particular location is 0, and while 100 means that my belief in the presence of a particular object in this particular location or particular pixel is 100%. So if you get 70%, this means that there is, you're more likely to believe that there's something there, right? And if you got like 30% or 20%, which is below 50%, then you're gonna use like approximation methods and, believe that most likely there's nothing there, but I'm not quite sure. But since LIDAR readings are very accurate, you'll probably either get 100 or 0. Alright, so we now need to save the map, right, using the map server. So we've got a node here. This is the map server package, and we get a node called the map saver, which saves our map. And we're gonna run that, right? And I really can't remember where the map is saved. I think it's saved in the home directory by default. And it's saved in the form of something called a PGM file, which is sort of, resembles a PNG extension or JPG extension for images, right? So it's a special type of file designed specifically for maps, and I think it's saved in the home directory by default. Right, let's just check it out. Let's run it. Right, so it's done. Yeah, here it said that it wrote the map occupancy data, and by occupancy mean it's a map that indicates whether each of its pixels is occupied or not. So this is why it's called. Sometimes a map is called an occupancy grid. Right. and it's saved to home map.yam. So yeah, so a map is saved in the form of a YAM file and a PGM file. Both extensions come out of this map server. So if I head to my home here, I'll find, yeah, I got map.yam and map.pgm, right? You'll find them here in my home directory, because this command by default saves my map in the home directory. And let's try to open up one of these files. For example, let's open this YAM file here. So yeah, it's saved in the form of an image having the extension PGM. So this is the location of the image, and this is the resolution. And by resolution, or resolution of the map, I mean that each pixel has, is in the form of a square that has like 5 centimeters side length, because 0.05 is in meters, so you convert that to centimeters, and it's like 5 centimeters. So you got pixels, square pixels, each of them having 5 centimeters. So you digitize the entire environment into a number of these pixels. And you've got the origin. So the origin of the map is -10, -10, and 0. That means that your x coordinate of the origin of this map is -10, and in the x direction, and -10 in the y direction. What this means is, for example, if we open up a whiteboard here, let's just try to, I think there is, right? I think I'm not allowed to use, an eraser. Alright, so I'm gonna just delete some of the drawings I had here. So basically what this means, if this is my environment, alright, and usually in Gazebo environments, the origin of Gazebo itself is located somewhere here in the middle, right? So this is the X and this is the Y, for example. So the origin of the map itself, or when you're, using the map server has, a picture format. So in picture formats, your origins, or the origin of the picture, is somewhere here, right? At the beginning or at the end, at one of the edges, right? At one of these vertices, right? So yeah, that's usually the case for PNG, GPG, and PGM and such extensions. Usually the frame, or the origin frame of that image, is located somewhere here at one of these vertices. And what basically says is that the origin of the image is like -10 meters away from the origin of Gazebo, and -10 meters away from the origin in Gazebo, in both x and y directions. So this is just to, offer some sort of transformation between Gazebo's origin frame, or fixed frame, and the frame of the image itself. Right? And let's get back to the YAM file. I think it was that one. Yeah. Negate, I'm not sure really what negate is, but the occupied threshold, this is the threshold after which you can say that this pixel is occupied, alright? So once your reading exceeds 0.65, and I believe that's 65%, I guess, because it divides the map pixel values by 100. In order to obtain some probability, because probability is between 0 and 1, so you have to divide 100 by 100, or divide your percentage by 100. So I think 0.65 here refers to the fact that once you see that your pixel is like, your pixel value exceeds 65%, then you can consider that this pixel is occupied. And the free threshold, so once you're less than 0.196, which is almost 19.6%, so you can consider that this pixel is free. Alright, I know I said earlier that it's 50%, but that depends on the algorithm itself. So for the algorithms I write myself, I usually pick the threshold 50%, right? But here the designer had another opinion, right? And it differs from one designer to another. So we gotta go with that, right? And if you open up the PGM file here, let's open it up. So we can find it's basically an image file where the unknown location has, like a gray value, because this is, like we say, a gray area, an area that I don't know anything about. and or I think the gray area expression refers to something that, yeah, is not quite, I cannot tell whether it's occupied or not. And we've got the black lines which represent occupied pixels, and we've got the white portion here which says that this area is basically totally white. That means there are no obstacles within this area, right? So this is the explanation of what we did so far, and I think, yeah, we're done. This was the last command here. So yeah, we're done with the implementation part. To sum up what we did so far, we defined the terms localization, mapping, and SLAM, and determined the exact intuition behind each of these terms and how localization, mapping, and SLAM work. And we launched Gazebo, and we constructed a global map using the gmapping package, which is a SLAM package. So we conducted both localization and mapping at the same time. And we constructed a global map which kept updating itself through continuous navigation through the environment. We also generated the map and saved it using our map server, right? And we saved it in the format of a YAML file which had some parameters defined, and another file which is called a PGM file, which is basically an image file, all right, which includes the details of our map, and we defined the meaning of the value contained within each pixel. So in the upcoming tutorials, we'll talk more of these simulation or SLAM and localization packages, and we'll also get to go through the navigation process itself. So we're going to define more terms, and we're going to be more familiar with robotic navigation.